Take it away, Halley.
Thanks, Chris. And as Chris mentioned, this is a preliminary work. And I think part of what I'm sharing is where it has sort of failed in interesting ways and where it has worked in interesting ways. So I'm really taking advantage of the fact that this is a place where we can share work that doesn't necessarily beat the state of the art baselines if they exist, but that is an ongoing sort of project to discover. So existing research on film and game score generation, there's no way I can go through all of it, but Plute and Pasquier have a pretty good description of content-oriented generative music. But in general, there's sort of deep learning-based music, which has drawbacks. Deep learning, until very recently, was unable to create coherent structures, and it's much more hard to control, except for with very small degrees of control. There's also film score programs that are generative in a very limited space. Like you choose a button and it chooses which of two predetermined pieces of music to play. But the music themselves are not generated algorithmically. There's also work based on using XML specifications, but without any underlying theory. And then because of that, the XML specification can be extremely cumbersome to use if you have to specify this has this this musical property, this has that musical property. It ends up being easier just to write the music. So what I propose is a theory of film music, and the goal is to have the ability to provide lightweight annotations and have them interpreted according to the theory of film music. So the input is specification and audio-less video, and output is audio for the video, which satisfies the specification. So how do we define a specification? A specification consists of a list of sets of scenic high-level properties and a list of durations. And for each S, every element of S is either defined by the background theory of film or a thematic variable. So let's take a step back here. We have scenes. We know what a scene is in film. That is pretty understandable. And we have these sort of high-level properties that we might associate with a scene. And then we also have the duration of the scene. All of these are pretty understandable even from a non-technical standpoint. So here's an example spec. And this goes into the defined by the background theory of film or a thematic variable. So we can have this spec that says that we have this character Jose and flamenco music for 8 seconds because something's going on that means that the music should sound like flamenco and Jose, the character, is present. Then we have Sally, who's another character. That's another thematic variable. There's no film definition, universal definition of what a Sally is, but a Sally is a something in this film. On the other hand, we do have a universal definition of what jazz is. And again, this is one of those oversimplifications that is a reason that this is preliminary work. But if you buy this idea that you can have this definition of what jazz is, but you can also have these sort of variables that are unique to a film, that you have a Sally who means something in the film, but not in the entire universe of films, then you can start developing these specifications. So the background theory of film involves a set of predefined Boolean or bit vector, fixed size array of Boolean bit vector variables U of S for any scene S. So basically we're going to define the composition of the scene in terms of these vectors which tell us things about the musical quality. So these include high-level variables, genre, suspense level, valence, happy or sad, mid-level variables, example, whether the violin has the melody, whether there's a high rhythmic density, and mid-low level variables, which involve specific rhythmic and melodic contours. Now, you could say that U of S should contain the low-level variables, the specific pitches and the durations. And the reason why I chose not to say that is because the generation right now proceeds in 2 stages. It produces these variables, and then it tries to approximate low-level variables. And the low-level variable generation is very poor, even though the mid-low level and high level generation is quite good. So I'd like to focus on this part of it, the high to mid low level variable generation. So for each instantiation of these variables, there exists predefined clauses. This is in an SMT theory, so satisfiability modulo theory. So there's the definition of the high level variables. Horror implies at least two of repetitive motion, dissonance, and symmetrical scales. These are just definitions you might find if you look at a dissertation on horror, the horror genre. Ontological properties, which sort of we know have to exist. That the violin has accompaniment implies there is an accompaniment, and ends on plagal cadence implies not ends on authentic cadence, because those two things we happen to know from music theory are mutually or from the definition of a cadence are mutually exclusive. The ontological properties, if we could go from the high level directly to the low level, we might not need them, because the constraint solver would know, oh, if it's accompanied, if the violin has accompaniment, that means I have to generate an accompaniment. But because we have this divide between the mid, high, low level variables, you need this sort of ontological properties. And then there are clauses for finding the musical mid, low level variables, the rhythmic and melodic contour. So building a piece of music, given S1 to Sn, create n copies of the variables in U and their independent clause is C. So basically, every scene is being defined independently. And then you add the background defined clauses from Si. So you add the, is horror to the clauses constraining the values of Ui. And you add leitmotif constraints between copies of C that have to do with the theme. So in the running example with Jose and Sally, we add a constraint that says that whatever Jose is, Jose has to appear, if the association with Jose has to appear when and only when Jose is one of the thematic variables. So examples of leitmotifs include a violin whenever a character is present and not when he is not, using a certain rhythmic contour whenever a character is present and not when he is not, using a certain high harmonic language whenever a character is present and not when he is not. This has to do with the sort of grander definition of leitmotif that was introduced by first by Wagner a lot earlier, but also in later studies of film music, in particular the music of John Williams. And there's a sense that leitmotifs can involve any musical element which is associated with a particular character or location or something like that. So to step back, in order to come up with something coherent, we need melodic contours. That's because we want to associate characters with contours, and because we want the overall part of music to be coherent. So we must have a certain degree of repetition and a certain degree of variation. There are also certain other rules that that are just understood by music theorists in terms of how the brain physiologically processes sound. That there are certain contours that are just not pleasant, and we want to avoid those. And the idea here is to make melodic contour into a subset of a regular language. So this probably could be a whole talk in itself, but I'll try to make it brief. Basically, melodic contour can be represented by a list of values, references, and transformations on references. So we have this. We have this part over here which says we're using the first reference. We're using 2-3 times. We're using the second reference. We're using the retrograde of the first reference, and here are what the references are. And this actually is constraining if you say that the complexity can only be a certain size, that the reference variables can only be 2 reference variables, and there can only be a certain number of transformations. So that piece that I was showing you here, it actually corresponds to one of Smetana's works. So this corresponds to the contour you see in the melody up here, and it can be read as the first pattern, which is a trifold repetition of a simple pattern, 0, 1 to the 3, followed by a trifold repetition of a simple pattern, 2, followed by the second pattern, so 1, so 3, 1, 2 is the second pattern, followed by a retrograde of the first pattern, followed by the second pattern with the third value augmented. So basically, there's this system for saying that melodic contours can be made up of patterns and transformations on patterns, but you're not going to do too many transformations and you're not going to introduce too many novel patterns. And this corresponds well to the idea that you don't want to introduce too much material, which is sort of a constant problem that is associated with sort of novices in music classes. So random versus generated melodies. Here's the one test. Is this significant? Let's hear something with a random contour and with a generated contour. Hang on. Unfortunately, I don't know if I can play. Hang on.
You need to share a tab, a Chrome tab, and then make sure you have the checkbox checked that says like share the sound from that tab.
Okay, so I'm gonna briefly stop sharing, and then I'm gonna share the Chrome tab. Thank you very much.
And there should be a little checkbox that says like include sound.
Yeah. Okay. So that was just random contour generated to fit within a C scale. And here is something that's generated using this sort of these sort of restrictions. And I'll talk about why they're not as different as we might expect, or one possible hypothesis. So I happen to like the generated version more. I don't know about you guys, but I'd say that it's not obvious which one is better. And the reason is that this is synthesizing the contour and then the duration's optimized for meter as opposed to joint optimization. And that's going to be a theme of my talk, is that it's harder to do things when you're jointly optimizing for a lot of things. It becomes more expensive from an SMT solving perspective. But when you don't jointly optimize things, it sounds worse, or it's worse from a quality perspective. Now, testing the significance of melodic contour constraints, there are two ways that I'd like to do that further to get quantitative ideas. One is user test of likability of things that are generated versus things that are random, but also what percentage of real themes versus random themes satisfy these constraints? Is it true that I showed this example from Smetana that satisfied these constraints? I have in my paper an example from Mozart which satisfies these constraints, but do most music pieces satisfy these constraints? That's a good question that I think I'd like to study further. Now, experiments I did for the jumping up one step or popping to the film scenario. I had 3 handwritten film scenarios, 3 existing film excerpts given new music, and 30 specifications randomly generated for determining statistics about the Z3, the SMT solver solving process. And here are some initial results. So here's an example where the low-level variables were handcrafted by me, but I made sure to follow the contour and mid-level variables generated by the algorithm. So I had the algorithm output the mid-level variables and the contour, and I wrote a piece according to that. And here's the result. So I just realized I missed a comment. First of all, the symbols describing the contours refer to sort of arbitrary contours. So basically, a 0 to 1 could refer to any situation where the first element is higher than the second element, which is also higher than the first element. So basically, 0 to 1 means that the second element is the largest, the third element is the first largest, and the first element is the smallest. So it describes relative sizes. So then you can project those onto scales. So in a C major scale, or in a if you want to take notes from a C major chord, that would be a 0 to 1 would be C G E. But if you wanted a minor scale, then it would be C G E flat. But they both have the same contour. And that's this idea developed by Robert Morris in some recent music theory. Also, I can't claim that was a good generated music demo because the generation part was limited. It was a algorithmically inspired demo because the low level notes weren't generated by the algorithm. The decisions that the composer was forced to make were decided by the algorithm. Now you'll hear some not so good, really generated music. So this time I won't have to tell you to notice, but you're going to notice a degradation in thematic and stylistic quality, even though there is some consistency in the themes. And this is end-to-end generation, so a human not touching it. So that's the same thing, but with having the computer generate the low level variables. And I think what that tells us is that the high level film theory can work if you have a human to interpret it. But getting those, even with those mid level variables, it's very difficult to get to a good low level evaluation. On the other hand, sorry. On the other hand, there were some things that I generated that were somewhat relatively interesting compared to other non-film music I've generated. So this is an example scored from the Harry Potter night bus scene, and this is done all from low level was generated. It's completely generated. So what I think is interesting there is that the imprecision of the second level specifications, and it's actually a two second level specification because it's specifications of 120 beat per meter bars, which is 2 seconds, is very noticeable. So the difference of timing between if it's 1.5 seconds off, it's very noticeable. And the themes are a little too short to be memorable, but I think it produced something kind of interesting from which I kind of like. So I wouldn't call this a complete failure. I keep doing that. Here is a example which sounds quite musical, but the it's not immediately obvious what the specification is from the music. Are there any questions right now? Awesome. Um, so it does produce some interesting results, but the relationship between the character desired and the actual quality is kind of questionable, which sort of brings up the question: is there a film theory? Are there things that automatically make something sound like Americana, or sound soaring, or sound like they're underwater? And you can go up to a video game composer and say, underwater, yeah, there's probably a marimba, there's probably a whole tone scale, but is that enough? And I think my conclusion from this exercise was, first of all, that by creating these sorts of specifications, you can create things that are musically interesting that you wouldn't create musically otherwise. Like, I enjoyed what I just listened to as a piece of algorithmic composition decently. But also that film music is more complicated than a few tropes. Um, it always does. So, for a post-mortem of what went wrong, there's tractability versus quality. And here's something where I could really get the SMT, satisfiability modulo theory, people in the room to give me some help. Because deciding rhythm with respect to meter as well as contour involves multiplication of multiple unknown integers and is practice intractable. That's just one problem that we have, is that we can't decide the rhythm with respect to meter and decide contour at the same time. That's very difficult. Um, Optimizing for melodic contours and scales jointly is very difficult. And so we've got this process where we decide instrument assignments, then contours, then rhythm, then melody, then accompaniment. And that makes things tractable, because the smaller you make a problem, the more it becomes tractable. That's just the nature of SMT solvers, is they're NP complete. So if you add two problems together, it's more than double as hard. And trying to figure out either ways to be systematic and smart about how we divide the problem, or ways to just boost the SMT solver, could greatly improve quality. There's the need for precision, that we're currently centered around every scene lasting a multiple of 2 seconds, and we need more fine-grained control to align the piece. And there's the probably necessary not sufficient conditions. So I don't think my definition of horror was ridiculous. I think the probability of horror, given that you have ostinato and dissonance, is much greater than the probability of horror given not ostinato and not dissonance. That it's probably necessary, or at least probably helpful. But that overall probability might still be small unless taking other factors into account. If you think of all music with ostinato and dissonance, there's a good amount of it that doesn't sound like horror. So so that's something that we need to work on, is sort of, is it possible to come up with sufficient conditions for defining something as horror? And would we want to come up with a single sufficient condition? That's sort of a pragmatic question. If we know there's a characteristic horror sound, should we always use it? There are also clear issues with integrating music together while maintaining stylistic aspects. Um, and that has to do with sort of the transitions between different styles of music, and that's another area that would involve probably another theory, is a theory of how to or a change to the theory is, how can we minimize the changes while maximizing the styles. So finally, opportunities for collaboration. I'd love to work with film music scholars on developing better theories in terms of, well, what makes horror, what makes Americana, what makes comedy. HCI scholars, I think, could be very helpful for a lot of things, especially learning how people react to the generated music, and learning how to respond to that by altering the theory. or just learning how to evaluate the theory. Type theorists. In the comments I got when I submitted this proposal, I got a lot of people saying, "Where's the type system? Where's the type system?" And you're right. It would be great to have a type system for the melodic contours, for determining what's a valid and invalid uh, uh, musical specification. And by the way, I didn't include this in here, but there is such a thing as an invalid music specification, which is where it returns unsat. The SAT solver returns unsat. And 80% of randomly generated musical specifications, where I just randomly chose different values, were unsat. But none of the actual specifications, which I wrote myself, were unsat. So there could be a type system which would enforce, no, this has to be something which is a reasonable specification. And finally, people who know how to make SMT systems tractable. That would be hugely helpful in furthering this project. And with that, I will come to questions.